Thank you very much, organizers, for giving me this opportunity. I will be presenting development of high-intensity proton accelerators, the present status and future program. So I will start with the introduction to high-intensity proton accelerators, then move on to the present status of development in BARC and DA units, then the technological challenges and our preparedness for the future. Then I will discuss about our medium energy high intensity proton accelerator program and then summarize. Well, so need for high intensity proton accelerator is already established in the previous talks. We need energy of the order of 1 GeV and currents of the order of tens of milliamperes in order to go for the ADS systems. Apart from ADS, there are other applications like base transmutation, base incineration, and such breeding applications. So we all know that neutron production per proton per GeV of energy saturates at around 1 GeV. So that is the optimum energy. If you are below that, neutron yield will be less. So we have to go for target the higher currents. Similarly, in order to have a reasonably good reactor of say 300 megawatt electric, you need to go for around tens of megawatt of the beam power. So that is our future goal, to go for accelerator of the order of 1 GeV and 10 milliampere current. Well, this is a typical slide which shows the different accelerating structures we plan to use. So the accelerator can be divided into two parts. The first is the normal conducting structures, normal conducting, and the other is the superconducting part. I am discussing about the linear accelerators, that also proton accelerator. So in the normal conducting accelerator, we use a structure called radio frequency quadrupole. The beam is produced by the electron cyclotron resonance, ECR based ion source. Then it goes to spoke resonators, drip tube LINAC up to 10 or 20 MeV. After that, there are superconducting cavities which are used, two different versions. One is the spoke resonator, other is the elliptical cavity. And then we are through to 1 GeV. So these are different stages. We have intermediate applications like RIB, radioisotope production, radio ion beams, which can be, the beam can be utilized at 100 MeV or 200 MeV also in between. Well, as far as our current roadmap is concerned, up to 10 MeV, we will be using drift tube LINAC structures, which are room temperature type. After that, superconducting structures will start. In the phase 1, we will go up to 40 MeV, followed by 200 MeV, and then 1 GeV. To give you an idea about the overall size of the accelerator, this will be longer in length actually, around more than 250 meters in length. Well, so I will discuss about the present status, what we are doing in BARC and DA. So our project for the BORM part, which is the normal conducting part, has already been completed with the completion demonstration of 20 MeV beam from low energy high intensity proton accelerator. So this is situated in BARC in CFB building. We have accelerated beam in several stages. The first milestone was 3 MeV, then up to 6.8 MeV, 11 MeV, and 20 MeV. We are injecting around 200 megawatt of radio frequency power, which is utilized to create the electric fields inside the structures. Accelerators are basically vacuum chambers, basically vacuum structures, where electromagnetic fields are to be created, which accelerates the protons to the higher energies. And 2 milliampere of beam current we have accelerated to the 20 MeV. This is to give you a brief idea about how these structures look like, starting from the ECR ion source, which use 1 kilowatt of microwave power to produce the plasma, and from there protons are separated from the other species. The ion source is in-house developed in BARC, and it can give more than 20 milliampere current. Then we have a low energy beam transport system, which consists of magnets and beam diagnostic devices, followed by a radio frequency quadrupole structure, which was a challenge in itself because it needed more than 100 brazing joints and with a lot of tolerances. I will be discussing briefly. This is followed by a medium energy beam transport system, which again use a buncher to compress the particles into actually narrower packets. This is followed by drift tube Linux structures, which is another variety of accelerating structure of slightly larger diameter, and which is efficient in this 10 to 20 MeV range. Well, so most of these technologies, all of these technologies have been developed either in BARC or with the local vendors, starting from ECR ion source, then radio frequency quadrupoles, drift tube Linux, regulated high voltage power supply, high power RF couplers, low level RF systems, beam diagnostic components, high power RF components, control interlock systems, and low conductivity water system. To give you a glimpse of these different technologies, this is the ECR ion source, where you can see a microwave source here, microwave line, which produces plasma, and then it is extracted with 50 keV of energy. The protons are separated from other species very efficiently, and we have recently got more than 60% proton fraction, which is as per international standards. We have been regularly using 10 milliampere beam out of this ion source. Two different varieties have been developed, 3 electrode and 5 electrode. We are right now using 3 electrode system. This is a radio frequency quadrupole system, which was designed in BARC and manufactured by BrahMos Aerospace, Trivandrum. Each section is 1 meter long. Total length of the structure is 4 meter. And this has more than 100 joints, which are to be vacuum braced in vacuum furnace. And vacuum leak rate should be better than 10 to the power -9 torr liters per second. Precision machining was required, and we have evolved after several iterations the successful brazing of these joints. This structure is capable of handling more than 550 kilowatt of RF power. Right now we are using around 530. The next structure is the drift tube Linux structure, which was also a technological achievement for us. Now the challenge here was to encapsulate the permanent magnets inside the thin copper tubes, which cannot be welded. Otherwise, the temperature of magnets will increase and they will lose the magnetism. Very precise alignment of drift tubes was required, more than 100 cells over 4 meter length. Such 4 tanks are used, giving total length of 16 meter. The quality factor achieved is, as per international standards, more than 30,000. And these structures are handling more than 1,400 kilowatt of RF power, radio frequency power. The high power RF couplers, which basically couple the power coming from the waveguide transmission system to the cavities, have been developed with the local industry, designed in BARC. Again, here challenges were successful vacuum brazing, because these structures again have to handle ultra high vacuum, as well as very strict dimensional tolerances were required. Well, on the front of beam diagnostics, we have developed almost all type of systems here with the local industry, designed in BARC. For example, this Faraday cup, this is an interceptive device, this cup goes into the beam line and intercepts the protons, and that current is measured. But all other devices, they are non-interceptive. Beam position monitor, fast Faraday curve, wall current monitor. They can capture the bunches up to even 500 picosecond or less. Regulated high voltage power supply of 100 kilovolt 25 ampere was developed within DAE and with the local vendors. This is 100 kilovolt 25 ampere power supply, and 96 modules of around 1.5 kV are integrated in series to obtain this. The bigger challenge was to have a less than 1% ripple, which was all achieved in this power supply. So we have a high power RF system here. Except Clystones, we have developed everything, designed everything in BARC and developed several local vendors. Low-level RF system again was designed and developed within BARC and with the local vendors. This is using basically digital technology to bring the amplitude and phase of the accelerating fields to within 1% of amplitude and phase. Well, this is a view of a Lehipa tunnel from where we extracted 20 MeV beam recently. This is around 20-meter tunnel, and we can see several feed points here. These are called RF couplers, and waveguide lines coming, total 10 feed points, feeding around 2 megawatt of radio frequency power to this, and beam is extracted at this location right now. We have used time of flight technique to measure the energy by putting two fast current transformers at the known length and measure the distance between by tagging the two bunches to know the beam energy. Well, this is a recent study which is very important because for high intensity beams, it is very difficult to constrain them into a smaller size. Otherwise, these beams may blow up. So space charge compensation is a technique where you inject nitrogen gas, dry nitrogen. And we can see here, we can see here that these bunches are getting narrower and narrower. Sorry. Yeah. Here we can see this bunch width is more, and when we are injecting this gas here at different flow rates, the bunches are becoming narrower and narrower. Well, so I will briefly just show these slides only. We have started utilizing the beam from Lehipa. This study has been done by Material Science Division of BARC on high entropy alloys, where we used 3 MeV beam to irradiate these alloys. These are our future plans to use this accelerator for studies on radioisotope production, and it can be used as a neutron source. We have plans to couple this beam to, that is being explored right now, to a critical facility where the neutron lifetime measurements can be done. Subcriticality can be studied at even 20 MeV with the modest current of 1 microampere average. Well, this is another plan. This slide is from Nuclear Physics Division, where we plan to do the radioisotope beam nuclear-based studies with this Lehipa. Well, now I move to the technological challenges and our preparedness for the future. Having demonstrated the normal conducting front-end injector of the 1 GeV, future ADS accelerator, which is the most challenging part, because here the beams have less energy and they are likely to diverge. The future challenge will be coming from superconducting cavities, which we'll have to demonstrate, or we have already developed also, I will be discussing. We have to develop long tri-modules. We have to develop cryogenic plant, high power RF couplers, RF sources, low-level RF system to control these superconducting cavities, superconducting solenoids, cavity processing facilities, and beam loss management will be crucial for high-intensity accelerators. Well, so I will touch upon one by one all these technologies which are required and what is our level of preparedness. Right now, we have a collaboration with Fermilab where we are participating in the R&D and construction of PIP2 accelerator, Fermilab accelerator. So under this collaboration, we can see that we are participating in almost all the components of a high-intensity accelerator. Starting low energy part, we have already demonstrated. Here, we are not involved in that collaboration. But in the superconducting part, India is collaborating for SSR cavities as well as elliptical cavities, cry modules, cryogenics, magnets, low-level RF amplifiers. So here, I will not repeat this. We have already done this warm part. These are the beam diagnostic devices which I have already discussed. RF electronics we have tested on LEHIPA, and the same with upgraded version can be used for the superconducting cavities. We have already tested them on horizontal test stand at RRCAT, and some of them have already been supplied to Fermilab and they are using it. Regarding superconducting cavities, we have completed the design, both thermal structural design, electromagnetic design of the cavity, which has already been reviewed by Fermilab experts. SSR cavity, superconducting spoke resonator cavity has been fabricated in India and dressed in CDM BARC. This cavity has achieved accelerating, the total gradient of 15 million volt per meter without any problem. And this is one of the best performing cavity which has been supplied to Fermilab or which is being used at Fermilab right now. The beam has been accelerated through this and this is being used there. So with this, we have confidence that we can make these cavities for our program. And these type of cavities can go up to 200 MeV of energy, SSR cavities. Regarding elliptical cavities, which will work at 650 megahertz, RRCAT is participating in this collaboration and they have set up all the required facilities for manufacturing, for the processing of these cavities and testing of these cavities. These 5-cell cavities have already been produced and sent to Fermilab also, and they have been tested to the required gradients and the quality factor. Well, we have in BRC designed and developed and supplied to Fermilab 7 kilowatt 325 megahertz RF amplifiers, and they are working in their PIP2 accelerator. Similarly, RRCAT has developed 40 kilowatt 650 megahertz amplifiers, which have been supplied to Fermilab. For magnets, we have developed both superconducting type as well as normal conducting type at BRC. They have been supplied to Fermilab and these are being used in their accelerator. So all these technologies which are required for our future program have been developed as standalone components. Some of them have been integrated to their accelerator. The challenge will come from integrating these to our accelerator in future. Similarly, on cryogenic front, we have our own program which is not directly dependent on Fermilab. This work is being done by Cryotechnology Division. And 4.5 Kelvin helium liquefier is already demonstrated. The work for 2 Kelvin cold box integration is going on right now. And all other technologies which are required for a 2 Kelvin helium plant, these have been developed by CRTD, Cryotechnology Division, with the help of local vendors. Now I move to our immediate future program is medium energy high intensity proton accelerator. So it started with 200 MeV design, physics design basically, which has already been published and reviewed. Based on that, now we have proposed a 40 MeV 10 milliampere accelerator at Vizag campus, which is going through various approvals right now. So this will be a 10 milliampere accelerator. Initially, we will be demonstrating 1 milliampere. 325 megahertz frequency will be used. And this will be using 2 cry modules, each housing 9 resonators. So up to 10 MeV, we will have DTL, which is room temperature. And after that, we will be introducing superconductivity. So basically, if you are able to go up to 40 MeV, then similar cry modules will be added. That is the beauty of linear accelerator. You can keep on adding the modules. And we will be able to go up to 200 MeV. Parallelly, RRCAT is working on the technologies beyond 200 MeV. And at some stage, they will be integrated in future. Well, so this is my final slide. For going up to 1 GeV, just to give you the numbers, we will need around 29 cry modules and 134 cavity resonators. So this will be the scale of the accelerator, which will be spread in around 250 to 275 meter length. So with this, I would like to summarize. So high energy, high intensity proton accelerators not only will be required for ADS, but there will be other applications, even at intermediate energies like spallation Newton source, or one can use it for waste transmutation, RIB studies. Successful demonstration of LEHIPA, which is a normal connecting front-end injector for 1 GeV accelerator, is an important step in this direction. Now we are embarking to demonstrate the indigenously developed superconducting accelerator cavities to be integrated to accelerator. LEHIPA is our immediate accelerator which we have already proposed. And along with IFC, we have made considerable progress in mastering the technologies required for full 1 GeV accelerator. And a very clear path forward exists for a 1 GeV accelerator. And no doubt there are significant technological challenges still existing, which hopefully we will be able to overcome in future. So with this, I would like to thank all of you.